Yeah, welcome back, everybody. Hope you had a good week last week. I'm pretty sure that you hated it, that we had to cancel everything last week. I couldn't produce and upload any podcast last week. It's just because I had what we call it in German, Seitenstrangangina. In English, maybe a side strain angina. That's pretty sure what the English word is for that. But anyway, it's affecting the throat, and I had a hard time to speak. Actually, I had to reduce the amount of speaking, which was probably quite good for my surrounding environment. But anyway, that's a different story. So yeah, that's why I couldn't produce anything last week. Meaning that this week is the last week of the lecture period, so we have to skip the graph section. Sorry for that, unfortunately, at least for the exam. I will try to produce some podcasts about graph data anyway, but that is explicitly extra material. So the Klausur, the exam in the first Prüfungszeitraum and also in the second Prüfungszeitraum will only be about the content so far, including this week's podcast, which is the remaining part on sequences. So we will stop after sequence data, and that is the content for the exams. Yeah, just that you know. And if I happen to produce some additional content on graph data, that is extra material. You are absolutely free to consume it or not, but it's not important or not relevant for the exam then. Okay, just that you know. Good. So let's jump in. We stopped at similarity models for time series, as you probably recall, and we already mentioned, that is the slide before this overview slide here. We also mentioned some popular similarity distances, and we'll have some similarity distances now in more at a closer look. So we'll start with simple similarity measures that do not consider the time axis as a thing that where things may go, where something may go on, so to say. Yeah, and afterwards we will have a look at more complex similarity measures, which, for example, is dynamic time warping, where we will have we'll do the time warp in that case. So let's jump in with the simple similarity measures. The first one is really simple, which is called the Minkowski distance, which is more or less the same as the Euclidean distance, or in general the LP norm. So the idea is that the representation of a time series is just an n-dimensional vector. A time series of length n is nothing else than an n-dimensional Euclidean vector. And if I have two time series, I can represent them, or I can take them as two n-dimensional Euclidean vectors. They should have the same length, of course. And then I can compute the Euclidean distance or the Manhattan distance, or in general the LP norm between those two time series. Yeah, you see that here, of course. That's the LP norm with you take basically the difference between the two time series in each time slot individually. Yeah, so you go through each time slot. The counter here is going from the first time slot to the last time slot, and you compare the values in each time slot with each other, and then to the power of p, sum them up and take the p root out of it. Yeah, so pretty simple. Obviously, you don't can have any distortion along the time axis and stuff like that, and of course you need time series of the same length. Yeah, but okay. Anyway, that's probably a good distance measure at the first glance. So here are some properties. Obviously, each time slot in X is compared to the same time slot in Y. Okay, we just mentioned that. Therefore, it's sensitive with respect to variations on the time axis. Maybe that we have more or less the same behavior of the two time series, but in X it is, or in Y it is just shifted a little bit along the time series. Yeah? And we'll see that later, some examples on that. But if we have that, we cannot account for that, because we simply compare each time slot in X with exactly the same time slot in Y. Yeah? So if you have any variations, distortions along the time axis, we have no chance to really take care about that. And it's, as I just said, limited, at least in the basic thing here, to time series having the same length, but also, of course, the same baseline, the same scale. Yeah. So even if time series have different scales, they have the same shape but different scales, we will see that here with large distances. Yeah? So if we just look for shape-based things, Minkowski distance is probably not the right thing. At least having the same baseline, having the same scale assumption, we can somehow ease that a little bit up, and that is on the next slide here. So if two time series, so this is the third property here, which is a kind of limitation, two time series having the same baseline, having the same scale, and having the same length. So what if two time series do not have the same length and do not have the same baselines and do not have the same amplitude scales, but have somehow similar behavior at least? Yeah. So let's just have the look at the different baselines and the different amplitude scales. So if we want to be invariant against those effects, well, we already saw that we could normalize, of course, the time series. We saw that in the pre-processing stuff we talked about. So for example, if we have the same, or if we have different baselines and different amplitude scales, we could do offset translation, so shifting the whole thing by the average value. We could do amplitude scaling through normalization by the standard deviation and stuff like that. And you see the effect here. So you have three stock price time series from three different stocks here, three different companies. So for example, if you just take this one here and this down here, they seem to have pretty much the same shape, at least, yeah. But of course they have different scales, amplitude scales. Yeah, so the Euclidean distance, for example, or the Minkowski distance in general, would be quite large, because from here to here, we will sum up all these differences here from here to here. Yeah? And if we just shift them by the average value, which is an offset translation, and maybe also scale it with the standard deviation, we'll have something like this here. And then the Minkowski distance will be much smaller between those two things here. Yeah? So normalization in that case could help you to find similar shaped time series with Minkowski distances, but still you have to be, of course, very, very careful when doing the pre-processing. Yeah? However, this is just for distortions along the amplitude spectrum, so to say. Yeah? What about if we have something along the time spectrum? First of all, if we have time series that have just not the same length but different length, well, of course we can also do some kind of shifting scaling along the time axis, and the easiest way here is just to do so-called upsampling or downsampling, yeah, in order to compare time series with different length. So we need some kind of scaling along the time axis, yeah, and that could be done by upsampling or downsampling. Upsampling, also meaning increasing the resolution, is okay. We just blow it up, so to say. Yeah? We increase the length of the time series, and we do that by simply repeating every value a given number of times, yeah, omega times in that case. Yeah, so we blow it up by a factor of omega. So from an original time series of length n, we get a time series of length n times w. Yeah, and we do that just by pumping up or repeating each of the original values here omega times. Yeah. That is upsampling, and downsampling is probably, obviously, surprisingly, the other way around. So in that case, we decrease the resolution, so only multiplies of omega are used. So in that case, we somehow decrease the length of n of the original time series by a factor of omega in that case. Yeah? So you see here a downsampling of this original time series here in that case. And we can use this upsampling and downsampling, one of those two, to compare two different time series or two different time series with different length using the Minkowski sum, the Minkowski metric. And the idea is just to scale both time series along the time axis with upsampling in that case to the same length, and then utilize the Euclidean distance. That is called uniform time warping, and you see the formula here. So here is that is the idea in words, and that is the idea in the formula. So we just use as a distance, we use the Euclidean distance between x and y, but we sample x up to or by the factor of the length of y, and we upsample y by the factor that is given by the length of x. And in that case, we end up in two time series having length m times n, and x is upsampled by m, getting from an m from a time series of length n with an upsampling of factor m, we get n times m elements here, and here we get n times m elements for m. And we normalize that here. So so that is basically the basic idea. And of course, instead of upsampling both, you could also downsampling one and upsampling two, for example, to meet the lowest common multiple or stuff like that. So you can do different things, but the easiest way to do it is just to upsample everything by the length of the other time series as a factor of upsampling.